Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. In this video, I'm going to discuss a parameter that's very important to understand when thinking about how solids dissolve, pHm. It's particularly important in understanding how acids and bases, and so by extension salts, dissolve in buffers. So, if you're ready to understand it, get yourself a drink and let's get into it. You would think that understanding how a solid dissolves in water would be easy. After all, many medicines are solids and they all need to dissolve before they can have an effect in the body. But the process of dissolution can be quite complex, especially when the compound dissolving is an acid, base or salt, because, as you may know, these types of compound will change the pH of a solution as they dissolve. To understand why this is important, we must first consider the process of dissolution itself. A particle comprises many trillions of molecules bound to each other. If the particle is crystalline, the molecules are arranged in a repeating pattern and are held together quite strongly by the crystal lattice energy. And if the particle is amorphous, the molecules are randomly arranged and held together much more weakly. In any event, in order to dissolve, molecules must break these bonds and form new bonds with water. I hope you can see that the only molecules able to break away and dissolve into solution will be those directly at the surface of the dissolving solid. These molecules must leave the particle to become solvated by water molecules before they diffuse away into bulk solution. The fact that dissolving molecules must first enter solution at the surface of a dissolving particle is very important, because it means the concentration of the solution must be highest in the region surrounding the dissolving particle. In fact, the concentration can usually be assumed to be saturated at the surface of the particle and will reduce as the distance from the surface increases because of diffusion of the solute. If we were to plot this as a graph, we would see something that looks like this. The region surrounding the surface of a dissolving solid, where the concentration of solute is higher than that in the bulk solution, is termed the boundary layer. It's very important to recognise that there is a boundary layer surrounding dissolving particles, because sometimes the way a material dissolves is different from what you might expect. And the reason is often that we must remember that molecules must dissolve in the boundary layer, not bulk solvent. It is also the reason why dissolution tests are usually stirred. The mechanical action helps disrupt and so lower the thickness of the boundary layer. So that means, firstly, that when a molecule leaves a solid and dissolves into solution, it does not dissolve in plain old water. Rather, it sees a saturated solution and can only dissolve when some already solvated molecules have diffused away. It also means, more importantly, that in the case where an acid or base, and by extension a salt, dissolves, the pH of the solution at the surface of the dissolving solid may be very different from that of the bulk solvent, because acids and bases change the pH of a solution when they dissolve, and the pH change will be maximised when concentration is highest. Again, we can visualise that as a plot so you can see what I'm talking about. The plot shows the pH of solution as a function of distance from a dissolving solid. And you can see that nearest the surface the pH is lowest. This is because I'm assuming an acid is dissolving. And as we move further away from the surface, the pH rises until it reaches a plateau in bulk solvent. We call the pH of the solution in the boundary layer the pH microenvironment, or pHm for short. Thus, we might assume that in this case, we would predict how a material will dissolve based on the molecules interacting with a solution of pH 7, but in reality, the molecules are interacting with a solution of pHm 3. Let me show you some real data to give you an example. On the screen, you can see data for haloperidol hydrochloride. The researchers dissolved haloperidol hydrochloride in various buffered solutions. pH is 7, 5, 3, 2 and 1, and expected to see very different dissolution rates because the drug is poorly soluble at pH 7 but more soluble at low pHs. In reality, they recorded very similar dissolution rates in all buffers. Why? Because the drug molecules are not dissolving into buffers at varying pH. The pH of the boundary layer, pHm, is between 1 and 3 in all cases, and the solubility is the same at these values. Remember then that any dissolving solid creates a boundary layer around its surface where the concentration of solute is higher than in bulk solution, and we term this region the boundary layer. Where a molecule changes pH upon dissolution, the pH of the boundary layer, pHm, can be significantly different from that of bulk solution. As a consequence, acids, bases and salts often dissolve at similar rates independent of bulk medium pH because the pHm value is similar. Right, I hope that makes sense. pHm becomes very important for salts when we consider stability in relation to pH max, but that's a topic for another video. If you liked this video, however, please hit the like button and consider subscribing, as it really helps the channel. Otherwise, thank you so much for watching, and I'll see you again soon.